The bright, warming sunlight that is hitting the Earth at this exact moment is exactly 8 minutes old. That light just crossed 150 million kilometers, exactly 1 astronomical unit, traveling at the universe's absolute speed limit, 300,000 kilometers per second. Because the vacuum of space offers zero physical resistance, the light sails across that massive void effortlessly, completing the trip in about 500 seconds. But this 8-minute sprint is just a footnote, the absolute easiest and final fraction of the light's actual lifespan. To see where that energy really comes from, we have to track it backward, moving away from Earth's atmosphere and returning to the physical surface of the Sun. The Sun's radius is roughly 700,000 kilometers. That is a tiny distance, less than 0.5% of the gap the light just crossed to reach us. If the Sun were transparent, it would take light only 2.3 seconds to cross from the center to the surface. Instead, it takes that light between 10,000 and 50,000 years just to cross that relatively short solar radius. How can a star, an object defined by its radiation, act as an inescapable millennia-long prison for its own energy? Deep inside the solar core, the environment is a chaotic storm of 15 million Kelvin plasma. The matter here is so crushed by gravity that it is 100 times denser than liquid water. This pressure forces protons to fuse together, releasing a massive burst of energy in the form of a high-frequency gamma-ray photon. This chart illustrates the energy barrier those protons must overcome. They fuse through a process called quantum tunneling. Quantum tunneling is a subatomic phenomenon where a particle passes through a physical or energy barrier that it theoretically lacks the kinetic energy to bypass. The moment those protons tunnel through that barrier, a photon is born, moving instantly at the speed of light. But despite that incredible speed, the crushing density of the core immediately halts its progress. Astrophysicists describe the interior of the Sun as having extreme optical thickness. Optical thickness is a measure of how easily light can pass through a material, with high thickness meaning matter is so densely packed that light cannot travel in a straight line. Inside the core, the photon faces an unimaginably dense soup of free electrons and ionized atoms, blocking every possible exit path. Because of this density, the photon is subject to a strict mean-free path. The mean-free path is the mathematical average distance a particle can travel before it crashes into another object. In the center of the Sun, that distance is just 1 single millimeter. After traveling a fraction of an inch, the photon crashes into a free electron and is absorbed entirely. The electron immediately re-emits the energy, but it spits the photon out in a randomized, unpredictable direction. Because that mean-free path is only a millimeter long, any forward progress the photon makes is immediately canceled out by microscopic diversions. This chaotic, zig-zagging movement is known in physics as a random walk. The core effectively functions as a 3-dimensional game of pinball, trapping light in localized loops. To finally escape, the photon must undergo an estimated 10 billion trillion separate absorption and re-emission steps. During these trillions of collisions, the photon gradually loses energy, shifting from a lethal gamma ray down into lower energy wavelengths like X-rays and ultraviolet light. This physics trap stretches a journey that should take 2.3 seconds into an ordeal lasting 50,000 years. The Sun's optical thickness acts as a cosmic regulator, trapping its own energy so it burns steadily for billions of years, rather than exploding all at once. Eventually, the photon diffuses far enough outward that the density of the plasma finally begins to thin. It eventually reaches the photosphere. The photosphere is the specific boundary layer of a star where the optical depth drops to 1, allowing the gas to finally become transparent. By the time the energy crosses this threshold, its trillions of collisions have cooled it into the visible light spectrum. After millennia in a subatomic maze, the photon finally leaves the dense plasma and enters the frictionless vacuum of space. This explosive moment marks the transition from a brutal physics trap to the sudden, total freedom of the solar system. It now begins its final 8-minute, 150 million kilometer victory sprint from the surface of the Sun to the Earth. When you stand outside on a clear day, you are the final stop on that trajectory as that specific photon strikes your skin. Every photon reaching you right now is a relic of the deep past. When this specific light forged in the sun's core, humanity was likely still navigating the last ice age. Every ray of sunshine is a 50,000-year-old survivor of a nuclear prison, ending its epic journey the moment it meets your eye.